All right, so yesterday we finished up talking about Bronsted-Lowry acid-base chemistry, but let's quickly go over that again because I want to reiterate these points. We said that if we start out with an acid HA and we've got this generic base B, that essentially this base right here will have these lone pairs grab a proton from the acid, and then this covalent bond will dump electrons onto A. So that covalent bond now becomes a lone pair on A. That gives A a negative charge, and it results in B having a positive charge. And we said that strong acids always form stable or weak conjugate bases, and strong bases form stable or weak conjugate acids. Then we went on to define the equilibrium for this acid-base chemistry, where we've got our acid reacting with water, and we knew we could write an equilibrium equation for this. We know that water's going to be a constant, so we can move that over, and we can define this as Ka. It's important to remember that chemists will occasionally use Ka, but we more often than not use pKa. So the pKa numbers are going to be the ones that I'm using from here on out, more or less. They're the ones you'll see in all the tables. All right, so let's talk a little bit more about the equilibrium that we're looking at here. And I'm going to redraw our example. We've got HA, that's our acid, plus B, which is our base. We've got this equilibrium where we've got our conjugate base over here and our conjugate acid. So let's label these. Got acid, got our base, got our conjugate base, and we've got our conjugate acid. The way I really like to view these equilibrium reactions is that we've got two acids present in equilibrium. We've got our original acid and we've got our conjugate acid. And these are essentially competing. Now we have to really look at each acid and determine which one's the stronger of the two. The stronger acid's going to push the equilibrium in the opposite direction. Let's make a note of that. The stronger of the two acids will push the equilibrium in the other direction. Does that make sense? It's kind of a battle between two acids. One that's stronger is going to shove it in the opposite direction more. So let's take an example. Pretty easy example at first, and then we'll go into harder ones. The first example I have for you is HCl. We're going to put this in with water, and then I'm going to put a box here. That's where our equilibrium arrow will go. We know that we'll end up with Cl minus, and what am I missing? H3O plus. So we know HCl is going to transfer its proton to H2O. That's the only option, really. Which side of the equilibrium do you think is going to be more predominant, the right side or the left side?
Right side.
Right side, just based on gut intuition, right? We know HCl is probably going to be a strong acid. So I'll put strong acid. H3O plus on the other side. That's also a strong acid, right? So we could go over here and we could say strong acid 2. So now we're kind of in this tricky boat where we know HCl is a strong acid, we know H3O plus is a strong acid, but our gut instinct is that the equilibrium should be on the right. This is a good case where pKa tables come in handy. And yesterday I showed you guys the Evans pKa table on the website. It's a really, really handy tool. So let's go down and look at our Evans pKa table. And on the left-hand side, we've got a big list of inorganic acids, and then we've got pKa's by functional group. What we want to do is we want to try to find our acid or the closest acid. So if we look down the inorganic acid side, we've got this guy right here, right? That's our hydronium. That's negative 1.7. And then down here, we've got HCl. That's negative 1.8. Sorry, purple's not the best color here. So let's write that up here. We've got hydronium, negative 1.7, and HCl is negative 1.8.
It's negative 8.
Or negative 8, sorry. Good catch. So pKa equals negative 8, and then pKa equals negative 1.7. Now we've got numerical values to back it up, right? This gives us evidence that HCl is a stronger acid because it's got the lower pKa. So in this case, what I often do with the equilibrium arrow is I say, all right, this top hand one, is going to be favoring that right hand side. And then the bottom one might be this little itty bitty arrow underneath. That kind of shows that this isn't a balanced equilibrium. It's lying almost exclusively on this right hand side. That's due to the HCl being a much, much stronger acid in equilibrium. So let's make a note down here. Pushes equilibrium to the right. Does that make sense? Remember, you don't have to memorize your pKa table, but it's a really, really good tool to have. So if you're ever in a situation where you're stuck looking at two acids, pull out your pKa table. You might not find the exact match, but you'll find a close match, and that's good enough. Oftentimes, estimating is the best you're going to do. There are other situations, though, where we simply don't have access to a pKa table, and we have to make some educated guesses or predictions, and that's what we're going to cover for the rest of lecture today, is how to predict relative acidity of various acids. And I know I'm drawing out this equation a lot, but let's do it again. We've got our acid in solution with our base, and we've got our conjugate base plus our conjugate acid. Oops, sorry, this should be a covalent bond. The first thing I look at with this equation is that conjugate base. This tells me, in my opinion, the most amount of information. So strong acids result in stable or weak conjugate bases. It's really easy to look at the acid itself and get really overwhelmed by it, but instead pluck off a proton like you did on the problem of the day and focus primarily on that conjugate base. It'll tell you a lot more. The other thing I wanted to say is various chemical features can stabilize our base, or our conjugate base. what chemical feature did we see in our pod that stabilized the conjugate base? Resonance, right? So that's an obvious one. If we can delocalize a charge, that's going to stabilize our conjugate base a lot. But there's other things too. There's a really nice mnemonic that Klein has in his textbook that I like using. Has anybody read ahead? A few people. Does anybody remember the mnemonic?
Oh, cardio. Wait, no, I made something else. That was my own.
Yeah, aereo. You're close. So it's ARIO. The first one is we always want to look at the atom. Second thing is resonance. The third thing we typically look at is something called induction, which we'll talk about in a second. And then the last thing we want to look at is the orbital. This is in order of most important to least important. So let's start with the most important chemical feature, and then we'll just kind of work our way down. So we'll look at the atom first. I'm going to box this off. So number one, look at the atom. There's two different things we want to look at when we're looking at the atom. First one is electronegativity. So I'll give you guys an example of that. We'll do, electronegativity. We'll do an example where we've got CH4 versus water, H2O. Imagine we've got separate beakers. In the first one, we're going to try to throw some strong generic base at methane, CH4, and we're going to do an equilibrium reaction with each of these. Let's try to figure out what our conjugate base would be for each of these reactions.
CH3 plus HB.
Close. So the first one, let's think about this. If the base is stealing a proton, it's stealing a positive charge, which means our conjugate base will have a negative charge, right? So the first one will have CH3 minus, and it has a lone pair. So that would be our conjugate base. And then we can draw our generic conjugate acid. What about the bottom one? OH minus, right? So we're going to pluck one of the protons off of water. We'll have OH minus. Let's throw on some lone pairs here. So again, we're going to look at this compound, the CH3 minus, versus hydroxide, OH minus. Which one's more stable? Hydroxide? Why? It's more electronegative, right? We've been talking about how more electronegative atoms are happier carrying a negative charge. So in this case, oxygen's pretty happy with that negative charge. Carbon's most definitely not happy with that negative charge. So this is more stable, since oxygen is more electronegative. That means that water must be the stronger acid.
Do we only compare the conjugate, or do we look at the original as well?
That's a good question. So the question was, do we only look at the conjugate or do we look at the original? I would say just look at the conjugate base in these cases. Ask yourself which one's more stable. The one with the more stable conjugate base is going to be the result of the stronger acid. That means water in this case is going to be more acidic than methane. Sometimes it's intuitive, other times it's not. So I always recommend drawing out your full acid-base reaction whenever you're stuck. It's a good idea and it's a good way to practice. What's something else that we could look at besides electronegativity? So electronegativity is that trend when we go left to right across our periodic table. What if we go up and down? What changes? Size, right? So electronegativity does change when you go up and down, but size changes dramatically. So size becomes a big issue. We'll do atomic size. And I've got a couple of them. Let's look at hydroiodic acid, so HI. We'll put this in water, or let's just do a generic base. We'll keep it the same. And we'll compare this to something like HCl plus our generic base B. And again, we'll have some equilibrium arrows. And we know HI can accept a proton, so it's going to be a donor. It means our conjugate base will be I minus. And we'd be left with HB as our conjugate acid. And in the bottom one, similar situation. HCl is going to give up its proton. We'll have chloride as our conjugate base. And we'll have our conjugate acid. Whoops. Which one's more stable with the negative charge?
Chlorine. Oh wait, iodide.
Chloride or iodide? Does anybody in the back have a guess? Back corner over there. Iodide? Why?
Because it's, or no, chloride because it's more electronegative.
So we could make that argument. We could say chloride's closer to that top right-hand corner, so electronegativity would say that it would be happier with the negative charge. But in this case, it's a little bit unusual. We want to look at atomic size. Which one's going to be bigger? Iodide. So iodide's going to be bigger. So there's another thing we can consider, that electron cloud, right? If we think about iodide as having this giant electron cloud and chloride having this small electron cloud, do you think that negative charge is going to be happier in a bigger electron cloud or a smaller electron cloud? Bigger, exactly. So the more room that negative charge has to occupy, the happier it's going to be. So the bigger atoms tend to be more stable when you're looking up and down a column. It's a little confusing because electronegativity in this case is only comparing atoms in the same row. When we're looking at the same column, then we look at atomic size. So that's one trend we always want to look at. So let's even make a note. More stable since electrons, or the negative charge, is in a larger electron cloud. That means in this case, HI must be the stronger acid. Does that make sense? So either compare two things on that same row or in the same column, but you always want to look at that atom itself. That's the most important first thing you should look at. Are there any questions with that? Yep.
So since it's in a larger molecule, doesn't that mean that the electron will be shielded more and stay more susceptible to electron repulsion in the nucleus itself?
Yeah, the way I always think of it is imagine you're a negative charge. You don't want to be forced into one location, right? We talked about that with our problem of the day. So if you've got this giant area to spread out in, this big electron cloud, you're going to be a happier electron than if you're confined to a small electron cloud. You're thinking about it correctly with electron repulsion, which if you have less area, those electrons aren't going to be as happy typically. So a smaller area would have more repulsion, and it's going to be less happy.
So the chlorine is a bit smaller. It's going to have a greater electron density, right?
Yes. So chloride in this case would actually be a better base than iodide. That's another way of thinking about it. Good questions. All right, let's take a look at number 2. So we'll go down to R. Sorry, let's scroll up. Number 2 was resonance. Which we already saw in our problem of the day. So let's take a look at a couple of examples. The first example I have is ethanol. The second example I have is acetic acid, also known as vinegar. Which protons do you think are going to be the most likely protons to be deprotonated? Do you think on ethanol, these 2 top protons up here will be more likely to be deprotonated, or do you think this proton on the right-hand side will be more likely to be deprotonated? Right-hand side, why is that? Yeah, oxygen's more electronegative. So we know there are other hydrogens we're going to look at, but in this case, that hydrogen is going to be the most acidic. That will be the proton that's lost. So same thing, let's draw our base. Generic B, have generic B. Got some resonance arrows. Let's even draw some arrow pushing. So in this case, this base is going to grab this proton. So I'll even circle it and say it's going to grab that proton, not its electrons. And this covalent bond is going to hop over to that oxygen. Let's draw in some lone pairs too so we can keep track of formal charges. Same thing down here. This base is going to grab this proton, and then these electrons will hop over onto that oxygen. So now we've got a conjugate base that has an oxygen with a negative charge. Created our conjugate acid. And then down here, similar situation. Got an oxygen with a negative charge. We've got HB+. So which conjugate base, this one or this one, is going to be more stable? Bottom one, right. Why do you think the bottom one? Because of resonance, right? I'm hoping I'm drilling this into you guys. If we try to delocalize these electrons, what's our problem? Texas carbon. We can't do that. We can't move that negative charge across atoms without resulting in a violation of the octet rule. However, with this one, we could say, oh yeah, we can move this down, we can move these electrons up. This has a nice resonance structure where that negative charge is actually shared by both oxygen atoms. So we can bracket these in. Oftentimes students will ask me, do I have to show both of them? Not necessarily, but if it helps you, definitely. I'll try to be specific on exams and quizzes what I'm looking for. So we know that this one, this conjugate base, is more stable due to resonance delocalization. That means that acetic acid, in this case, must be the stronger acid. Make sense? Reiteration of our problem of the day. Always draw out that conjugate base if you're ever confused. All right. What was the next one after resonance? Induction. This is a new one for us. So we'll do number 3. This is induction. Another way of thinking of induction is it's a polling of electron density. through sigma bonds. And I'll show you guys a couple of examples. They make a fair amount of intuitive sense, but let's take a look. So the first one I've got is a fluorinated compound. So these are pretty cool. So we've got 5 fluorines coming off of the carbons. And we'll have a base hanging out over here. And then we'll compare this to the carbon or hydrocarbon analog. So one where we have assumed hydrogens, not fluorines. Same thing, we can say, all right, this base can grab this proton. This covalent bond will now hop over to oxygen and form a lone pair. Do the same thing down here. All right, we'll draw in our conjugate base. Got fluorine, fluorine, and the 3 fluorines over here. And then this one looks similar, but no fluorines. If we look at these, we'd say, all right, the negative charge is on the oxygen in both examples. So it's a tie at that atom level. And then we could check for resonance, and we could say, can we delocalize the lone pair? No, not without forming a Texas carbon on both of them. So there's no resonance. But if we think about fluorine versus hydrogen, fluorine's the most electronegative element on the periodic table, right? So which one do you think is going to be happier bearing the negative charge? The top conjugate base with the fluorines on it, or the bottom one? Top one, right? So in this case, we could say, well, there's a big pulling of electron density towards these fluorines, so we could even do a dipole arrow. And that will stabilize that negative charge a lot more than the example on the bottom. So we would say this one's more stable. Due to inductive pull by fluorine. That means up here that this must be our stronger acid. All right, I've got a problem I want you guys to think about and discuss with your partner. Let's do a challenge here. All right, in the first example, let's do it this way. Do bond line notation. I've got 2 fluorines up here versus this example, which is an isomer, where we have 2 fluorines over here. Which of these 2 do you think is going to be more acidic? I'll give you guys a minute, but talk about it with your partner and see if you guys can come up with a consensus.
Taking away some of the electron density from the oxygen.
Where's the other one? Can't go.
Not as strong because there's not as strong as that.
Yeah, they do large types.
Put a thumbs up if you think you and your neighbor got it. Some consensus. Some more thumbs up. Does anybody want to offer their rationale for why one's more acidic? What do you think, Kelsey?
I think that the right one will be, because in the right, the fluorines are pulling the electrons away from a carbon and a hydrogen, versus the left, they're pulling it from two carbons. Hydrogen is a little bit less electronegative than the carbon on the carbon.
Okay, so you're arguing that the position of the fluorines might matter. Does anybody have a different view? I think that's a good idea to think about, all right, that fluorine's pulling in multiple directions as opposed to just one direction. Different idea? Let's go with Anthony right now.
Well, it's like you said, the fluorine, the location of the fluorine matters, but I think because on the second one, the fluorine is going to pull that charge over the entire molecule, whereas the first one is going to pull it over to that part of the molecule.
So you think the one on the left or the right is going to be more acidic?
The one on the right,
On the right, because the fluorine's only pulling in one direction?
it's pulling over the entire length of the molecule.
Okay, it's pulling over the entire length of the molecule, so you think this one's going to be more acidic.
No, the right one.
You think this one will be more acidic?
Yeah.
All right. Does anybody else have a different explanation? How about in the back?
I think the one on the left.
On the left? Why do you think the one on the left?
On the conjugate base, the fluorines are closer to the oxygen, so they're more likely to exert a more inductive force on the non-functional electrons.
I think that's a really interesting idea. So you're saying that on this one on the left, if we pluck off that proton, we've got a negative charge that's closer to the fluorines?
Right. The other ones, the other fluorines, they have carbons and hydrogens in between them, so they're not as likely to have any effect or as much effect on them.
Yeah, I really like that. So you're saying the distance from the fluorines really matters. This is entirely correct. The analogy I like to use is the inductive effect is like a vacuum cleaner, right? If you're close to a vacuum cleaner, you're going to feel it. The further away you get, the less you're going to feel it. So that inductive effect actually drops off with distance a lot. So in this case, the compound on the left is going to be much more acidic. Since the fluorines are closer to the negative charge. Think about a vacuum cleaner hose. That's how I got it stuck in my head when I was learning this. Closer you are to that vacuum cleaner hose, the more you're going to feel it. In fact, once you get a few atoms away, the inductive effect is almost non-existent, or it's very, very minimal. It drops off very rapidly. Let's draw in some dipole arrows here. So we know that this dipole is going to pull up electron density there. This one's going to pull it over a longer distance, so that dipole is going to have a harder time stabilizing that negative charge. All good ideas, though. Sometimes these inductive effects can be a little tricky. All right, last one. After induction, we had hybridization. Oh, yeah, orbital. Sorry, orbital hybridization. I don't want to throw off our mnemonic. If we had an H at the end, it wouldn't sound very fluid. All right, so let's compare methane to acetylene. All right, we'll have our generic base, and we'll do some equilibrium arrows, and we'll try to show the movement of that proton. So first one, the space will grab a proton for methane, We'll take only the proton, not the electrons, and then this covalent bond will get dumped over onto that carbon. Same thing down here. We'll pluck off this hydrogen. That covalent bond will end up on carbon, and we'll get our conjugate bases. All right, so we've got our two conjugate bases, and then I'll fill in our conjugate acids. So if we look at these, the conjugate base has a negative charge on carbon in both cases, so the atom portion of a Rio is tied. Neither of them can do resonance, so we're at a tie with R. Induction, don't really have that. There's no electronegative atoms on here. That leaves us kind of stuck. That's where orbital hybridization comes in. Let's think about the negative charge here. What orbital is it in? Oh,
Well,
it's,
it was sp3 now.
let's think about it. What's the steric number? 4, right? We've got a lone pair plus 3 bonds. That's the steric number 4. That means it's going to range into what shape? Trigonal pyramidal. That means it's going to be sp3 hybridized. All right, so that negative charge is stuck in an sp3 lobe. All right, the one below. What orbital is that negative charge going to be located in? SP, right? We're at a steric number of 2. This is a little abstract to think about, but who remembers what lobe is stubbier or shorter, the SP lobe or the sp3 lobe? SP, right? It's got more S character. It's going to be more spherical-like, less oblong-like. So this one's going to be a stubbier, that's the scientific term, lobe. That means the negative charge is going to be held closer to that carbon nucleus, right? That negative charge in this case is actually happier when it's held closer to the nucleus. So let's circle this. We'll make a note. More stable since the negative charge is held closer to the nucleus. That has to do with the greater amount of S character. That means acetylene, in this case, with the triple bond, is going to be the stronger acid. It's a little abstract, but that's kind of our last resort thing that we look at when we're assessing the acidity of various molecules, is what orbital are we pulling the proton out of, and where's that negative charge going to reside in? Because I know you guys like exceptions, I'll tell you the one exception.
Is that the exception to orbital or to the rules?
To orbitals and the overall list of rules. So we'll do NH3 versus acetylene. Again, if we've got generic bases here, we could say, all right, let's imagine ammonia losing a proton. That would mean it would be NH2 with a negative charge plus our conjugate acid. And if we pulled the proton off of acetylene like above, we would end up with an acetylide ion where carbon has a negative charge, and Hb plus. Using our Rio rules, right, we would say, well, immediately, that nitrogen we know is more electronegative than the carbon. That means our gut instinct would say, this should be more stable, and ammonia should be the stronger acid. This isn't true. It's a weird exception where in this case, NH3 is a worse base even though it is more electronegative. So in this case, orbital dominates.
You mean worse acid?
Oh, sorry, yeah, good catch. Worse acid.
When you say worse, do you mean weaker? Like, is that what worse means?
Weaker acid, weaker or worse acid, it doesn't want to give up that proton. So in this case, ammonia is a weak or poor acid, even though that nitrogen's more electronegative, and that's because orbital rules dominate. This is the one exception to the Areo rules, and it's something you might see in your sapling assignments or in various homework problems. All right, I think that's where we're going to end off today. Tomorrow when we come in, we're going to look at identifying the most acidic proton on various molecules. So we'll have to use some of these rules.